Welcome to section 3-4, exponential and log equations, where we're going to be solving for x's and y's. Two biggies to remember here, the one-to-one properties that we've been studying. If the bases are the same, you can just set the exponents equal. If the log of this is equal to the log of that, then this is equal to that. And we also have inverse properties, just like squares and square roots. Here is a log base a. If we give that an overall base of a, so now it's a to the log base a power, those are going to cancel, and the answer is just x. And same thing here, we've got log base a of a to some power. The base a and of a here are going to cancel, and the answer is just x. Our other inverse property, those are going to be very useful here. And this example one, you don't have to write anything down. It's just sort of like a recap of some of the stuff we've seen and what properties being utilized. So here, 2 to the x is 32. You rewrite it so the bases are the same. Set the exponents equal. One-to-one property. Here we've got the log of this is equal to the log of that. So we can set the x equal to 3. One-to-one property. Here we can flip the fraction, make the exponent go negative. So that would be 3 to the negative x. Rewrite the 9 as 3 squared. X is negative 2, one-to-one property. E to the x is 7. We would take the natural log of each side. The natural log of the left, natural log of the right. Here, the natural log of e is going to cancel, just leaving the x. X is the natural log of 7. We use the inverse property. Now here, ln of x, I'm going to rewrite this one down here. ln of x equals negative 3. Well, we want to get that x freed away from the natural log. And to do that, we need to give it a base. We need to make this an exponent, so we are going to exponentiate. We're going to base e both sides. So here now the e and the ln cancel, leaving x equals e to the negative 3. X equals e to the negative 3, inverse property. We can do the same thing here. They've got log of x equals negative 1. Well, remember the log here, the common log has a base of 10, so we will exponentiate. Give this a base of 10. As long as we give the other side of equals a base 10, everything's good. 10 to the log base 10 is going to cancel, so we'll have x equals 10 to the negative 1, or we could write that as 1/10. Inverse property. The last one here, we've got a log base 3 of x is equal to 4, so we would just exponentiate. Give this side a base 3, and this becomes 3 to the 4th power. So the 3 log 3 cancels, and we've just got x equals 3 to the 4th power, or 81. Again, that was an inverse property application. So we got some strategies here. First, rewrite the original equation in a form that allows the use of one-to-one properties of exponential and log functions. Rewrite an exponential equation in log form and apply the inverse property. Or you could rewrite a log equation in its exponential form and apply the inverse property for exponentials. The more you do, you get a feel for it, and they become easier and easier. See here in the first one. Okay, it looks like this is a one-to-one property. We've got a base e is equal to another base e. So since the bases are the same, we can set the exponent negative x squared equal to the negative 3x minus 4. I like my x squareds to be positive, so we're going to add that to each side. So now it's x squared minus 3x minus 4 is equal to 0. And now that we've got it equal to 0, we can factor it. See, we need x and x to get the x squared. The numbers that multiply to negative 4 and add to negative 3 would be minus 4 and a plus 1. And then we would set each of those factors separately equal to 0. And we're going to get x is negative 1 and x is positive 4. Okay, the directions did say round to 3 decimals if necessary, I think. That one we didn't need to go decimal, but that tells me this next one we might. So we've got a 3 times base 2 to the x power equals 42. Before we address the base 2, we got to get rid of the times 3. So let's divide both sides by 3. So now we've got our 2x all alone, and that's equal to 14. Okay, now there's a couple ways to go about this one. If you look in the textbook, they would do this. Since we have a 2 over here, they're going to do a log base 2 of the left side. And, of course, we would have to do a log base 2 of the right side, 14. And when we do that, the log base 2 of 2 is going to cancel, so our left side would just now be an x equals. And then we've got a log base 2 of 14. We could use our formula and rewrite that as the log of 14 over the log of 2. And then we could just take that to the calculator. You squeeze it in down here. X would be approximately 3.807. Now again, the book went this route here with the blue stuff. An alternate way would be to just take the natural log of each side. I could take the natural log of the 2 to the x power, and I could take the natural log of the 14. And now we've got my favorite property of logs. We can bring this exponent down front. So now that becomes x times the natural log of 2 is equal to the natural log of 14. And then to get x alone, we would divide both sides by the nat log of 2. Now remember here, if you punch this in your calculator with the log logs and this one with the natural logs, when you do divide, we will get the same answer, 3.807 approximate. So for a lot of these, there's different avenues you can take to get to the right answer. Here's some for you to try. This first one would be based sort of like on example 1. And the second one down here would be based on the example we just finished up. So pause the video and give those a try. See what you can do with them. Okay, now there are multiple ways to do the first one. Without checking the book, I just did it with like a change of base formula. But that 512, it's kind of hard to see. But we've got 2 to the x is, 512 is 2 to the 9th power. And then you could just say x is equal to 9. What I did, though, I took the natural log of each side, the ln of 2 to the x power, and of course the x can come down front. And we would take the natural log of 512 and then divide both sides by natural log of 2. So if you punch in your calculator nat log of 512 over the nat log of 2, it will divide out to a nice clean 9. All right, next one. Let's see if I can, oh yeah, sweet. So this is a log base 6. So to solve this, I'm going to exponentiate each side, give them each a base 6. So now the 6 to the log base 6 cancels. I've got x equals 6 cubed. 6 to the 3rd power is 216. Okay, that's B. Letter C. The first thing I would do is add e to the x to both sides. So now we've got e to the x is equal to positive 5. Let's get rid of that base e with a natural log. We'll nat log both sides. So now we've got x equals the natural log of 5. And the book just left the answer like that. We could get a decimal, but I like the exact answer a little better. On this last one here, I believe, what are we going to do with this one? Oh, okay, I see a base 3 here in the denominator, and we've got a 9. 9 is 3 squared, and we already had an x up there, so that'll be 2 times x power. Over here, it's 1 over 3 to the 1st. Let's bring that denominator up and make the exponent switch signs to negative. So now we've got the bases are the same. Set the exponents equal to each other. Divide by 2. X is negative 1/2. Excellent. A couple more down below here. Just like the last example we did. Base e equal to base e. The exponents, or the bases are the same. So we can set this exponent equal to this exponent. And my x squared is positive here on the right side, so I'm going to keep the x squared there. We're going to subtract the 2x. Now that'll go in the middle. And then we've got a minus 8. And let's factor that. What numbers multiply to 8 add up to negative 2? That'd be minus 4 plus 2. Yeah. And then set each of those equal to 0. You'll get x equals a negative 2 and a positive 4. And let's see the last one here. This we'll probably have to take to a decimal, just like in the example. So first off, we can divide both sides by 2. And now we've got 5 to the x power equals 32 divided by 2 is 16. And now, well, we could log base 5 each side, or we could take the natural log of each side. I'm just going to do the ln of each and bring the exponent down. So now it's x times nat log 5 equals nat log 16. Divide both sides by nat log 5, the natural log of 16, over the natural log of 5. And that decimal is approximately 1.723. 1.723. Okay, we got another one. Okay, example 3. Solving an exponential equation, solve round to 3 spots. All right. So I see an e to the x. We want to get that alone. So let's get rid of its buddy plus 5. We will subtract 5 from each side. 60 minus 5 is 55. And now we've got the e to the x alone. Let's natural log each side. So the natural log and the e will cancel, leaving just the x. And x is the natural log of 55. If you're into decimals, that would be approximately 4.007. And there we go. That one wasn't too bad. Maybe the next one will be worse. Oh, it looks like it's going to be. Let's get this beast under control and round it to 3 decimals. All right. So I see the variable is above this base 3. So we want to get this term alone and then address getting rid of that base. So let's see, to get rid of the stuff around it, we've got to get rid of this minus 4. So we're going to add 4 to each side. 2 to the 3 to the 2t minus 5 power equals, we're going to add that, so that's equal to 15 now. And now we've got our base 3 in this set of parentheses. We got to get it out of there, so let's divide by 2. So now we have our base 3 to the 2t minus 5 power. That's equal to 15 halves. 15 over 2. All right, well, at least on the left side, we've got the expression with our variable isolated, that base 3. So there's a few ways we can go about this. Let me try to stick with the book and look in my notes here. Yeah, okay. Oop, get over there. The book would say to log base 3 each side. I'm going to switch to red ink so it stands out. Since this base is 3, we could do a log base 3 of that side, as long as we do a log base 3 of this side. All right, on the left side, the log base 3 of 3 all cancels out. So we're just left with our exponent, 2t minus 5 equals. Now here, we could separate this, but we do want to get a calculator answer at the end. Now I'm going to do something I'm usually not too keen on doing. I'm going to turn that fraction into a decimal. 15 over 2 is 7.5. 7.5. We don't want to punch that in the calculator now and round it and use that in more computations. We only want to log at the very, very end. But we're getting close there. Notice the 2t we want to get alone next. So let's get rid of this minus 5. We're going to add that to each side. The log of 7.5. And then after that, a plus 5. Now to get t alone, we're going to divide by 2. T equals, and instead of dividing by 2, I'll just write it as a 1/2 log of 7.5. Plus, we got to divide the 5 by 2 also. Let's go decimal, I guess, 2.5. And now that we've got the t by itself, now it would be a good time to punch this in the calculator. I would type in the 7.5, take the log of that, times it by 0.5, add 2.5 to that decimal, and if everything goes well, t should be approximately 3.417. Okay. I think there's just a couple checkpoints for you to finish this video off, and that will be it for day 1. Here you go. Pause the video and give them a try. All right, the first one shouldn't be too bad. E to the x, let's get rid of the minus 7. We'll add it to both sides. So now that's e to the x is equal to 30. To get rid of base e, we nat log. The nat log of e goes away, so we just have x equals. And we natural log the 30, because we got to do that to be fair. If you like, they did ask for the decimal, so that'd be 3.401. Excellent. Last one. just like our last example, there's going to be a little bit going on here. It's going to take a few steps. Oops, made that pretty big. Get out of there. All right. So remember, the big idea is we want to get this term alone. So what we're going to have to do is minus 4. So this is going to turn into 11 minus 4. That's going to be a 7 over there. And then we are going to divide by this term to get it alone. So that's going to be a 7/6.